All right, first off, we're starting off by continuing from here. So here was, where is it? My pen. Heron's Huron's formula. Um, I find I found some information that might be from one of these countries first, but all the texts are like such a blurry mess that I don't know which one. Same thing with most of the other ones. Like I can't tell. I'm not sure if this is the first one, but this is the first one I found that made sense. And over here, I think it's Euclid that made this first, not Pythagoras or whatever. I I'm questioning that, but I'm not a math historian. If someone wants to correct me, go ahead. Um, anyway, this is one proof that takes forever. So I'm gonna give you this, but if you want to prove this, go ahead. It's not as hard as you think it is. It's just expanding this and then making sure it's the same as the left-hand side and right-hand side. Uh, that's the way I would do it to prove that. Um, I don't want to do it, so I just gave you that given. I also gave you this given. Now, with this given, you have to rearrange it. This is the law of cosine, as we all know. For multiple times, I have stated this one. So we want the cosine to be the main focal point because the area of a triangle, what we're going to use is the area of a triangle with 1/2 BA sine C. So what that gives you is a squared plus b squared minus c squared divided by 2ab for a triangle such that has this. Um, yeah. So triangle that we have, any random triangle, not a right triangle, random triangle, and then you put a altitude here. And after that, you bring up this definition again that we keep on referencing. We keep on referencing because it's useful. But if you square this side and square this side, you get a formula that has a sine square. Why on earth would that be important? Because we can use the Pythagorean identity. The Pythagorean identity, one form of it is this. So we can plug that into here as 1 minus cosine squared of c. Now, obviously speaking, any angle would have worked. We define A, B, and C, and I chose to go with C first because to me, uh, I don't know why. That's the angle that we chose. But you could have chose the angle A, angle B. It doesn't matter. It will just change the altitude of it. I can't say it correctly sometimes. Anyways, I'll show you a little bit more change of the definition section because I realized geometry has a lot more definition than I thought I would need. Um, it's kind of annoying how much definition you need. Forgot about it entirely. So in the end of the day, if you simplify this to this, you can get this formula, which turns into this by the given over here, because I didn't want to prove that. And from that, you get this. Okay? And from that, we can just do a little bit of algebraic manipulation, just a tiny bit, a minuscule amount, to get this format over here. And now finally we get Hermann's formula. I can never say his name correctly, so I'm not even gonna try. Anyways, altitude is this basically, and here's one example solution of it. Now this proof I don't ex Actually, this might be possible. I gave you the answer already. So if you're given this, cover up the highlighted parts and you were given this, I think you could have proved that. It'll take forever, especially if you're a high school student, but you could probably get that, honestly speaking. Yeah, and there's a little bit more here. I'll explain this part later. But before I do that, I almost forgot the changes I have given to the definition section, which is over here, which I added the parallel, the perpendicular, the therefore, and the triangle, and the similar, just because I totally forgot about it. I really forgot that those things exist. AKA, don't think so anyway. Similarity triangles now haven't. I mean, similar triangles I have, but I don't know. But yeah, triangles I have used, but I haven't used those like notations ever. That's what I meant to say, notations. Not that I'd never used triangles before. That would be a complete lie. Anyways, so from here, we're going to prove this fact, this fact, this fact, and this fact next. And how we prove that is similar triangles. And at this point of time, we did this multiple times, so I'm just cutting it a little bit. But we know from earlier that we can get that this triangle is equal to this triangle. Um, uh, did I? Here's one way to look at it over here, which I know is like there's another right triangle, but you can kind of that doesn't work actually. Uh, no. So did I ever explain this? Yeah, no, law of sine and law of cosine. In there, there's one, so there's a trivial solution over here. Yes, a trivial solution over here that explains that. If you look carefully, that trivial explanation was the reason why it works. Uh, yes, the trivial explanation is the reason why I explained it over here also. You know, so here's the length, and this is 90 degrees. And then this over here is 90 minus the angle, which equals this angle over here. And then this, if that's true, because of 90, this angle must equal that angle. Yes. And then from that, you can say side, angle, side. Oh, yes, side, no, angle, angle, angle. It would be an angle, angle. So there's two angles, which means they're similar. You only need two, not angle, 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 just two angles to make it similar, and therefore there's two angles that are similar. Therefore, we got it. Anyways, from this over here, this is A, B, D, and A, B, C, over here, the big two. We can get AB, which is, where's AB? Fuck. AB is this, I think. And then AB and AD over here. As you can see, uh, it's just a lot of matching AD to AC over here, and then that would mean this fact over here. You can kind of look over here to see if it's true. Why this is important, I have no idea, but I know I use this one for one of the proofs. I've never used this in my life yet, so other than learning in geometry. So here's a question. Yeah, and I'm pretty sure you can prove each one, but uh, I already proved it with two angles, right? Anyways, so over here is the Pythagorean reciprocal version. So we know that this is true. E over here and A over here, oh, not A. A over here and D over here is true. Now we know this from earlier. So now we combine those two to get this form. And you might be wondering, how did I get from here to here? Well, in resistor, I just thought of a resistor because in a lot of times when you have a resistor, you get this form when you have this type of question. So I knew this off the bat in my head, but um, this is a classic resistor question. Um, but if you didn't know that, you could have I guess you couldn't have realized it, but uh, you can multiply uh, d square. It's not obvious actually, because and then you just add those up and you realize that. But it's not obvious. I'll try the right hand side to get to this form and reverse engineer it, which is a way to do it. The other way you could do it is partial fraction decomposition, which I don't want to do, so fuck that. Next thing here, 90 minus theta. So over here, there's 90 and minus theta. That gives you ABD over here, the angle, right? And then over here, we get 180 to total triangle. We get minus 90 from this. And then that gives you this angle again, which allows you to figure out that this angle must equal this angle on this case too. Excuse me. So I guess the other question was when I had it like this, it was more like this. So chopping it like that. You use that in physics one, AP physics one, and physics 2A or 4A. And then we have some basic vector that you can use. We're going to go to vectors again. This is more for just the direction and everything. It's just a starting. It's not really maybe I should put it in trig. I'll think about it. I'm still thinking about it. And then we're finally back to this and having to do these proofs. These three proofs I'm going to change to the format I like later. And then we're going to circles. Circles is an infinite polygon. It has infinite amount of size, basically, is what the polygon. Oh, wait. Oh, wait. I'm going to stop here.